Welcome to Chem 314 Carbohydrates Video 1. And in this video, really, we're just going to introduce you guys to some of the terminology. I think that's how you spell terminology of carbohydrates. And we will also introduce you to the Haworth or ring structures of simple carbohydrates. And this video is going to focus only on monosaccharides. Our next video is going to focus on di and polysaccharides. So first of all, let's just define what's a carbohydrate. So a carbohydrate is any biomolecule with the formula that is approximately CH2O repeated n times, approximately. Sometimes you can have other elements in there like nitrogen or sulfur or phosphorus, but for the most part it's just carbon, hydrogen, and oxygen. Now the simplest of all carbohydrates are the simple sugars or monosaccharides. Here's what you need to know about simple sugars. These guys have 3 to 7 carbon atoms each. They have precisely 1 carbonyl. So in other words, they're either going to be an aldehyde or a ketone. Although sometimes you can't see the carbonyl. More on that in a second. And all of the other carbon atoms, other than the one with the carbonyl on it, have 1 hydroxyl apiece. Trying to write an I on there for apiece, and my pen is just not collaborating with me. All right, so these are the simplest sugars or monosaccharides. And by the way, that term sugar, that just means any small carbohydrate. It doesn't have a precise definition. Any small carbohydrate that tastes sweet, which is most of them. So, the hardest thing to get to know about carbohydrates is the terminology, okay? And also those structures that we draw for them. They kind of all look the same at a glance, but there is a system to it. So if our simplest sugars are 3 to 7 carbon atoms long, and they've got 1 carbonyl, then that means that you would draw them as something like this. Right? So there's our carbonyl. This is a 3-carbon sugar. This is called glyceraldehyde. Or if you wanted to draw a somewhat more complicated sugar, you could do something like this. All right, so there is our carbonyl. And notice that our carbonyl is always going to be on carbon 1 or on carbon 2 for any carbohydrate that we're going to see. So as you can see, based on these structures that I drew, that these molecules have lots and lots of chiral centers. And so keeping track of those chiral centers becomes a real challenge. And so that's why usually when you draw a carbohydrate molecule, you don't draw it like this. You draw it in one of these formulas down here. These are what are called the Fisher projections structures of your carbohydrates. And the reason we draw them that way is because it makes it really easy to see where each of your OHs goes. In other words, what's the configuration at each one of those carbon atoms? All right, so we said that monosaccharides can be either aldehydes or ketones, and they can have 3 to 7 carbon atoms apiece. So we have special terms for carbohydrates that are aldehydes versus ketones, and we have special terms based on how many carbon atoms they have. So if your carbohydrate has 3 carbon atoms, it's said to be a triose, and those are the ones that are shown at the left here. Now this one on the far left is an aldehyde, and this one over here would be a ketone. And so our terms for those would be aldose, and the ketone version would be ketose. And you can combine these two terms together into a single word. So for example, glyceraldehyde over here is an aldotriose. Glucose is an aldohexose because it has 6 carbons. And you can keep going like this. Stop me if it gets too exciting. All right, so there is kind of a shorthand way that you can write Fisher projection structures for carbohydrates. I'm going to give you guys an example. If you wanted to write out a full Fisher projection structure for a carbohydrate, it would look something like this. That's kind of a pain, so I write them in a more of a shorthand manner. These two structures show the same thing. Right? Each cross represents a carbon atom. And so we have a chain of 5 carbon atoms. Our carbonyl is at the top. CHO means aldehyde. And then each of the other ones have an OH on them. So for this particular monosaccharide, you can see that we have 3 chiral centers. Now, this last chiral center at the bottom, this one down here is kind of special. So this is our chiral center that is farthest away from the carbonyl. That one we call the DL center. And in every carbohydrate that we are going to see in this class, we have the D configuration. And what does that mean? That means that the OH at this position is on the right. That's assuming that you put the carbonyl at the top. And so just like for amino acids, almost all naturally occurring amino acids have the L configuration. Almost all naturally occurring monosaccharides, and essentially everyone that you're going to see in this class, is in the D configuration, just the opposite. Now, this may be a chiral center, but we said that it's pretty much always going to have the OH on the right, because essentially all carbohydrates are in the D configuration. But we still have 2 other chiral centers, and those can have different configurations. So if you were to flip the configuration on one of those, so that now we have, say, the OH on the left in that position, now we have a different sugar. So the one at the left is D-ribose. And by the way, you're not expected to know the structures of all the different sugars. That's pointless. This one over here is considered a different substance. This one is called D-arabinose because it differs in configuration at that chiral center right there. So these 2 sugars are an example of what we would call epimers. That means they differ in configuration at 1 chiral center, not the DL center. If you were to take your original ribose and invert the DL center, so that you had the OH on the left, like that. At this point, you have L-ribose. It's still considered ribose. So in other words, it's only those chiral centers up there that determine the name of the sugar. So L-ribose and D-ribose are not considered epimers because they differ at the DL center. But all of these different structures are diastereomers. And you should remember what that is from organic chemistry. So now that we've got that out of the way, let's take a look at what sugars actually look like, because as it turns out, they do not usually look like I've shown them on this slide. All right, so it turns out that sugars most of the time form cyclic structures. In other words, they're rings. And the reason for that is because they have a carbonyl on them. The carbonyl group is pretty reactive. And what happens is that the carbonyl group can react with a hydroxyl group on the same molecule to form a ring. And generally, that's what happens. So 95% of the time, your carbohydrate molecules exist in a ring structure and not in a linear structure, okay? But this reaction is reversible, and so they can always go back to being a linear molecule like we see at the left. So for example, in fructose, this OH group can undergo a nucleophilic attack on that carbonyl carbon up there. A ring forms, and you're left with a ring structure over here. So if your ring structure is 5-membered, and so that would be 4 carbons and 1 oxygen, you have what's called a furanose structure. The opposite, or not the opposite, but the alternative, I guess, would be a 6-membered ring, which has 5 carbons and 1 oxygen, and that's called a pyranose. And notice something. The oxygen that was part of the OH, that ends up as part of the ring. The oxygen that was part of the carbonyl ends up as an OH, and it's always on the outside of the ring. So it is possible for most sugars to form more than one structure. So for example, fructose, which is what's on the screen in front of you, that can form 4 different possible ring structures. So it's got 2 different possible furanose structures and 2 different possible pyranose structures. So why 2 different? Well, you'll notice that over here, there's this one carbon atom that has an OH on it. And that OH can point down or it can point up. It depends on which way the carbonyl is facing when it gets attacked by the other OH group when the ring forms. And these can interconvert reversibly. So they are not considered distinct substances, they're considered distinct conformers. So these are examples of what we would call anomers. So anomers are ring sugars, so we should say rings. They don't exist for linear sugars, that differ in configuration at the former carbonyl carbon. We call that one the anomeric carbon. And these can interconvert. So that would be our anomeric carbon. It's easy to spot the anomeric carbon in any ring because it's the only carbon that is bonded to 2 oxygens. And so you can see that this carbon is bonded to that oxygen and to that one, so it's the anomeric carbon. Those ring structures that we were showing you on the previous slide I need to talk about the way we draw those for a moment. These are what we would call Haworth projections. And they give you the structure of a monosaccharide when it exists as a ring. And the way that they're drawn tells you a little bit about conformation. So what is this sugar molecule? What does this look like? What we're saying here is we have a six-membered ring, and you should think of this as we're viewing it at sort of an angle, so that the carbon-carbon bond at the bottom is kind of pointing out of the page at us, and these other ones at the back are facing away from us. And then all the other substituents are above or below the plane of the ring, which is a bit of an oversimplification because this thing isn't flat. It's not aromatic or anything like that. But that gives you an idea of how the whole thing is configured. So that's what we would call a Haworth structural formula. So the standard way to draw a Haworth formula means that you have the anomeric carbon on the right and the ring oxygen in the back. That's how we usually draw them. And if you are in the standard form of a Haworth projection, then you can distinguish between the alpha or the beta anomers of your monosaccharide. Okay, the alpha anomer means that the anomeric OH points down, and the beta anomer means the anomeric OH points up. So in this case, I drew it as the beta anomer. That's our anomeric carbon right there. That's the convention anyway. However, you always want to be careful because sometimes to make our structures more pretty or more compact, we don't draw them in the standard form. Sometimes we draw them in different forms. So just be watching out for that. Another thing that you need to notice about Haworth formulas is they tell you about configuration, but they don't so much tell you about conformation. These rings are not flat. In reality, just like with cyclohexane, there's some stagger going on. And that means that at the ends and at the corners, these groups can either stick up above the plane of the ring or hang down below it. And so those substituents that are sort of in the plane of the ring, those are said to be equatorial, and those above and below the plane of the ring, those are said to be axial. And so each sugar has one sort of favored chair conformation, and that's the one that has all of the bulkiest groups mostly equatorial, because then they're spread out, less steric hindrance. And that ends up being important for the properties of polysaccharides, which we're going to see in video 2. So for practice, see the carbohydrate worksheet, which is up on Canvas. And in video 2, we're going to talk about polysaccharides.